Welcome to the Distance Learning Lab for Soils 201. Today's lab is going to be on cation exchange and soil pH. Previously in class we've talked about these two chemical characteristics of the soil. Soil pH is a measurement of the hydrogen ion concentration that's in solution in a soil at a given point in time. As you can see from what I've written here on the board behind me, we're measuring the actual concentration of hydrogen ions that are in solution. This concentration will vary based upon what other types of chemical processes are occurring in the soil at that point in time. We will be measuring pH today in the lab with a pH meter based upon what is referred to as a saturated paste extract. When we measure the pH of this soil using a saturated paste extract, the first type of pH we will measure is what is called active acidity. Active acidity is taking into consideration only those hydrogen ions that are in solution at a given point in time. Another form of acidity which occurs in the soil is called reserve acidity. We will also approximate or measure the reserve acidity of the soil today. We'll do that by taking the same quantity of soil and mixing it up or forming a saturated paste extract with calcium chloride solution. Now when we do this, we would normally expect a calcium solution to cause that pH to be perhaps slightly higher or more towards the basic level side of the scale. However, we need to understand that when we add the calcium chloride solution to this soil, what is going to take place is an exchange reaction. That is to say that the calcium in the calcium chloride solution, because of a very high concentration, will go into and kick off the ions that are being held on the exchange sites currently on that particular soil sample. Now, this is to be an acidic clay loam type of soil. Because it is an acidic clay loam soil, the major cation that will be displaced off of these exchange sites will be hydrogen. So as this calcium chloride or saturated paste extract with calcium chloride is equilibrated, and then we measure the pH of that particular saturated paste extract, we will expect to see the pH go down instead of what we might have thought is going up. The reason it will go down is because we will have removed the hydrogen ions from the exchange sites, which are not being measured as a part of the active acidity, but this will give us an idea at least of what level of reserve acidity is occurring in that soil. Why do we want to know the pH of the soil? Well, as I've indicated earlier in the lecture portion of this class, pH is a primary determining factor as to the solubility of nutrients and therefore the availability of nutrients to plants from that soil. If we needed to modify or change the pH of that soil, in most cases we would be looking at trying to raise the pH, causing that soil to be less acid or bringing it into a range more desirable for plant growth. When we try to neutralize the acidity of a soil or raise the pH, we need to understand we are not just trying to elevate the active or to offset the active acidity of the soil, but we are also trying to offset the reserve acidity. Because as we go in and lime a soil, which is a normal type of amendment used to raise soil pH, when that soil is limed and we increase the soluble calcium content in the soil, that calcium will go on to exchange sites. This is true, and it will also increase its concentration in solution. But in order to get that calcium onto those exchange sites, we will be displacing hydrogen from these exchange sites. Therefore, we have to help not only neutralize hydrogen that's in solution, we also need to take into consideration the level of reserve acidity in the soil, or also help to neutralize the hydrogen that was being held on these exchange sites. The other thing that I would like to point out is that the pH scale is a log scale. It runs from 0 to 14, with 7 being neutral, below 7 is acidic, and above 7 is basic. Each unit that we move on this pH scale gives us a change in concentration of the hydrogen ion by a factor of 10. So in other words, if we have a soil at a pH of 7, and that pH over time were to go to 6, that same soil with a pH of 6 would be 10 times more acidic than that soil with a pH of 7. To elaborate on this further, if we move the pH on a soil from 7 to 5, that is a unit or change of 2 units on the scale, we are changing at a factor of not just 2, but from 7 to 5 is a factor of 10 to the second power, or a total of a 100-fold change, in this case a 100-fold increase in the concentration of hydrogen ions in that soil solution. Another way of saying that is that a soil with a pH of 5 is 100 times more acidic than a soil with a pH of 7. So keep in mind that the pH scale is a log scale, and the significance of that is that each unit move on the scale changes the concentration of hydrogen, or if we're thinking of that in terms of the degree of acidity of the soil, by a factor of 10. Other than soil pH, the other chemical property of the soil that we're going to be measuring today is cation exchange capacity. I've listed a few notes here on the board for cation exchange capacity. We can define that as the ability of the soil to hold and release cations between the soil particle surface and the soil solution. Cation exchange processes involve holding of ions on the surface of these soil particles on these negative exchange sites. That could be a soil particle, it could also be a humus particle as a part of the organic fraction. Those exchange sites will always be full, but they are going to be in balance or in an equilibrium with what is occurring in the form of those ions in soil solution. So we have a balance here between those cations which are occurring in solution and those cations which are occurring on these negatively charged exchange sites on both the mineral particles in the soil as well as the humus or organic matter particles in the soil. In this laboratory exercise, we're going to be measuring this by a replacement reaction. In other words, we will be, in one case, utilizing distilled water, which does not have a concentration of ions in it. It's distilled or deionized. We will be leaching a soil sample with this. The purpose of that is to remove any soluble calcium which occurs in that soil and get it into the leachate. In the second soil sample, we will be leaching that soil with a concentrated solution of potassium chloride. Now this potassium chloride, because of its high concentration in solution in that soil, will drive off those cations that were being held on the exchange sites and replace them, of course, with potassium, the cation which is a part of this solution. We will catch the leachate from that soil sample, and then we're going to add a couple of drops of concentrated ammonium oxalate to this particular solution, or to that leachate. The reason for the ammonium oxalate is that it is going to complex with any calcium that we've leached out of that soil sample and give us a precipitation reaction. So the potassium displaces calcium from the exchange sites. We estimate the quantity of calcium held on those exchange sites by a precipitation process, and that's where the ammonium oxalate comes in. Calcium combines with the oxalate portion of this molecule to form an insoluble precipitate in this aqueous solution. We will estimate the amount of cation exchange capacity there based upon the quantity of that cloudy or white precipitate in this aqueous solution. So those will be the two exercises that we perform in this lab today. Soil pH of both a saturated paste extract with distilled water and a calcium chloride saturated paste extract, and then cation exchange, estimating the quantity of cation exchange in the soil by a leachate process, and then precipitating the calcium in the solution with another ion, in this case the oxalate ion from the ammonium oxalate solution. So with that introduction, let's move to the determination of soil pH first.